Alright, so in this video I'm gonna be explaining another important article with the title Learning Long-Range Dependencies and Graphs via Random Walks. So this important paper in 2024 from Max Planck. So message passing graph neural networks, while excelling at capturing local relationships, often struggle with long-range dependencies. Conversely, graph transformers enable information exchange between all nodes, but oversimplify graph structure by treating them as set of fixed-length vectors. This work proposes a novel architecture, neural walker, that overcomes the limitations of both methods by combining random walks with message passing. This is very interesting. If you combine random walk, it's like the asynchronous message passing pattern you see in your brain. So neural walker achieves, this is really interesting, combining random walks with message passing, exactly like your brain. Asynchronous, finds its past, sometimes going back to the nodes, revisiting the node, and then continue. This is what happens inside our brain, but unfortunately AI is totally in a very different direction, which is not bio-inspired. That's why the computational complexity of AI is terrible. But this bio-inspired architecture, which is asynchronous message passing, this is what is happening in your brain. So it's a random walk, at the same time it's a message passing. We are combined. That's why they call it neural walker. So most graph learning methods, as I said, they face this long-range dependency problem. You see here the message passing captures degree centrality. We have many different notions of centrality. One of them is degree, very, very simple, degree centrality. While random walks capture subgraphs, like cycles. So let's reflect on this. Message passing is like that, random walk is like that, so why not combining them? So they propose a novel framework that leverages both of them. And you can integrate it with any kind of GNN or graph transformer architecture. You can integrate, for example, GIN with special type of graph transform. So this is an overview of neural walker. The random walk sampler samples m random walks. This is an important step. Once we get these random walks, without of course replacement, the walk embedder, the next step is walk embedder, computes walk embeddings. It's like a sentence generation. You take a sum or average of word embeddings of all of them. After you do embedding or, for example, skipgram, any algorithm that you use, then you do embedding. All of the walk is embedded in just single vector. Then you have sequence layer and then walk aggregation. Because different walks are coming from different paths. So the walk embedder computes walk embeddings given into node embeddings at the current layer. The walk aggregator aggregates walk features into node features. So walk features, now we are going to node features via pooling. Via pooling of node features encountered in all the walks passing through the node. So you see walk embedding here, it has position embedding plus edge embedding plus node embedding. Then we have walk embedding. Then we have walk aggregator. Because from any starting node, you can have many different walks. So we aggregate all of these embeddings, and it's also related to sequence modeling. So we propose this neural architecture, neural walker. They're proposing their article in 2024. A random walk sampler independently samples a subset of random walks on each graph through a probability distribution on all possible random walks. For any distribution on random walks, it's a realization of MIID, identically independent distribution samples, and our model is always operating on such realizations. So we use additional encoding features that store connectivity information captured during random walks. We consider an identity encoding, which encodes whether two nodes in a walk are identical within a window, and an adjacency encoding, which includes information about subgraphs induced by nodes along the walk. So our walk embedder in each walk block, encoder block, generates walk embeddings given the sample walks. So now we are using this node, and this one is the node embedding, this one is the edge embedding at the current block. And the index I plus 1, I. Now, because that's I, so we are talking about the I's entry of this walking. We are talking about HW of I. The I's entry can be calculated like this. The I's entry. It's a walk like W1, W2, W3, W, for example, a walk of length K. Then at each instant, for example, I3, we can calculate using this equation. We can calculate the embedding of that using this equation. So the neural network is learning, this walk embedding is learning this pattern. This is even better than skipgram, that some articles that use anonymous walk embedding, they use that because you are combining all of them into a single module. You don't need to do some pre-processing using skipgram and then come back to the original model. It's a single unified module. That's why it's interesting. A sequence layer transforms a sequence of feature vectors into a sequence, a function. And so 1D CNNs are simple, fast models that process sequences. They are GPU friendly. And transformer models are widely used. I think this is a state space models that is still in its infancy in comparison to other models like transformer, CNN. So let's focus on this walk aggregator. We have a sequence of walk, we go through each walk, and now we have walk aggregator. Isn't it amazing? This is the walk aggregator. And this is a good idea. That's why it's in 2024. You will see in 2025, this year, you will see many such ideas. And one could also average no edge features in the walk, passing through a certain edge to update the edge features. We also use skip connections to keep track of the node features from previous layers. Now that we have walk aggregation, now we connect the paradigm of this random walk to message passing paradigm of graph neural network. Now you see they are the same thing. You can integrate them very easily, very beautifully using this beautiful equation number 3. So this is how you update it. You aggregate, give it to message passing, because each node has many receiving messages, and then you aggregate them. And after a local message passing step, one could also apply a global message passing to incorporate global information into nodes by allowing all pairs of nodes to exchange information. So let's have a reflection to see what are the disadvantages of this modeling. So after local message passing, one could also apply global message passing to incorporate global information. That make it more complex, but it's better to be simple. Otherwise, we cannot explain it. The explainability problems becomes so hard. So I think this is not necessary, but they introduced it in the modeling. And then HTV is represent virtual node at block. So they use the idea of virtual nodes for long distance and then theoretical results. And they did some tests on these benchmarks. This is a good benchmark. This is specially designed, these two specifically designed for long distance to make sure that your modeling is good. So neural walker still is not as good as GCN. Of course, they are almost the same, but I'm saying that there is no improvement. There's nothing more than GCN still for long-range dependencies. And so driven by limitations of pure walk-based encoders, this study investigates whether message passing can provide complementary information. We conduct an ablation study to compare, and then holding the sequence layer fixed, neural walker with message passing consistently outperform version without confirming that random walks and message passing offer complementary strengths. Notably, local message passing consistently improves performance, suggesting its effectiveness in capturing local context and centrality information. The benefit of global message passing, however, varies across datasets. Interestingly, large graphs like Pascal show a more significant gain from global message passing. So I have a playlist about domain adaptation. The distribution of your graphs is very critical in all of your performance, in all of your publications. But that's why people use many datasets, many benchmarks. Because in some benchmarks you have good performance, in some of them have worse. That's a natural thing, because your modeling has some cons and pros, definitely. And so this is the summary of the data sets that they used.